Why is this floating nuclear, the Ford-class aircraft carrier, replacing the legendary Nimitz-class ships? And how does its complex system of decks and layers manage to accommodate almost a small nation's air force in the middle of the ocean? But the most important question is, why did they replace the old steam catapult with this costly electromagnetic rail system that can launch 4 aircraft in under 60 seconds? And, in the age of drone warfare, can this massive warship truly defend itself with these close-in weapon systems? More detail, all in the video ahead. The Gerald R. Ford-class aircraft carrier was built at a cost of $13 billion and is one of the largest in terms of deck size. How big? Well, for comparison, the Nimitz-class aircraft carrier looks almost the same, but the Ford's deck size is much larger. Let's break it down further. The Ford has around 25 decks, or layers, spanning from the bottom of the hull to the top of the superstructure, while the Nimitz class has about 18 decks. These decks, or layers, span vertically through the ship's hull and superstructure, showing a significant difference in size and capacity. This size difference gives the Ford class an advantage. It typically carries up to 90 aircraft, while the Nimitz class generally accommodates around 60, though maximum configurations for both can exceed these numbers. That's roughly a 30 aircraft advantage. All of this is largely due to the Ford's larger, more open hangar bay and wider flight deck. To give you a better idea of how the Ford accommodates such a large number of aircraft, most are stored in the hangar bay, which is directly below the flight deck, the top level used for takeoffs and landings. The hangar stretches across roughly 2/3 of the ship's length and provides space for storing, maintaining, and preparing aircraft when they're not on the flight deck. The flight deck itself covers about 4.5 to 5 acres, roughly equivalent to 3½ to 4 American football fields in length, and up to 1 football field in width. This immense area allows the carrier to accommodate and operate up to 90 jets and helicopters at maximum capacity. So, the Ford's jet storage is mainly on the hangar deck beneath the flight deck, and the total deck area is about the size of 4 football fields laid end to end, making it one of the largest moving structures ever built. The Ford accomplishes this with 3 large aircraft elevators. The forward elevator near the bow helps move aircraft quickly to the front of the flight deck for launch and parking. The midship elevator near the midpoint of the ship acts as a central hub to shuttle aircraft between the hangar and flight decks, reducing congestion. The aft elevator near the stern assists in positioning aircraft for maintenance, recovery, or parking at the ship's rear. Unlike the Nimitz-class carriers, which have 4 elevators, the Ford class has 3 larger elevators. This stems from a better and more open layout enabled by the smaller island structure moved further aft, freeing up more usable flight deck space for more efficient aircraft handling and operations. But what makes the Ford class better is the addition of the electromagnetic aircraft launch system, which uses electrical and electromagnetic principles to accelerate aircraft smoothly and efficiently off the flight deck, replacing the older, rough steam catapult technology that the Nimitz class has been using for the last 4 decades. To help you understand how it works, let's walk through the process. The Ford-class advanced nuclear reactors generate electrical power, which is stored temporarily in capacitors or kinetic energy storage systems. This stored energy is ready to be rapidly released during aircraft launch. When the launch command is given, the stored electrical energy is converted from direct current, DC, to high-frequency alternating current, AC, by power converters. This tailored energy powers a linear, synchronous motor system embedded along the flight deck track. The aircraft's nose gear then connects to an electromagnetically driven shuttle on the catapult track. This shuttle acts as the physical interface that moves the aircraft forward. Here's the most important part, and the reason steam power was replaced. A sequence of electromagnets along the track is energized with precise timing, controlled by digital software. These magnets create a moving magnetic field that smoothly pulls and pushes the shuttle, accelerating the aircraft according to a programmed acceleration curve. Once the aircraft reaches takeoff speed about 155 miles per hour, or around 240 kilometers per hour, the shuttle releases it and the aircraft lifts off. The shuttle then slows down electromagnetically and returns to its starting position, ready for the next launch. You might wonder why the Navy chose this costly upgrade over the tried and true steam catapults. The answer is simple. Electromagnetic takeoff provides smoother acceleration, significantly reducing stress and wear on aircraft frames compared to the harsh forces of steam catapults. Most importantly, the electromagnetic aircraft launch system is far more versatile. It can launch a wider range of aircraft weights, from heavy fighters to lighter unmanned aerial vehicles, with precise control, making it a game-changer for modern naval aviation. This advancement makes the Ford-class aircraft carrier not just a vessel of power, but a platform equipped with cutting-edge technology designed for efficiency, safety, and adaptability. During flight operations, this deck is considered one of the most dangerous places in the world to work. Together, they can launch about 4 to 5 aircraft every minute. But wait, these fighter jets' exhaust is extremely powerful. So, just before takeoff, the jet blast deflectors are raised upward at a 45 degrees angle using hydraulic cylinders. This is done to prevent the extreme heat from damaging the high-value assets stationed nearby. Interestingly, the Queen Elizabeth class does not have catapult launch systems. This is also similar to Russian and Indian carriers. Instead, it relies on the tried and tested ski jump process to launch its fighter jets. However, what goes up must come down. And this is where this American aircraft carrier stands out. It features not 1, but 4 steel arresting cables, also known as cross-deck pendants, spanning this small moving airport. Upon touchdown, the aircraft's tailhook connects to one of these cables, bringing the aircraft to a stop in approximately 300 feet. That's a significant amount of stopping power for a fighter jet of this size. Just like an airport, it has a flight control island, also called the airboss. It is from this deck you can have an almost panoramic view. Just below it is the navigation bridge. In simple words, the captain and his crew steer the movement of the 12 billion airport. Moving further ahead is the radar room. Just below the radar room is the Combat Direction Center on an aircraft carrier. These are specialized spaces that provide information for command and control for close-in support systems or the Sparrow missiles. This is the nerve center of the ship, providing processed internet information for command and control of the near battle space. The radar programming and software on the Gerald R. Ford-class aircraft carrier allow it to process massive amounts of information instantly. For example, when small killer drones are detected flying toward the flight deck, the system can quickly identify the most important threats, coordinate multiple weapon systems, and engage them by firing the close-in weapon system, phalanx guns. This automated process requires much less manual control compared to older aircraft carriers, making the Ford class much more effective at neutralizing fast, small threats. To help you understand more about the tech behind America's latest aircraft carriers, you can learn from Brilliant's growing collection of programming courses. This is a great way to build timeless problem-solving skills to thrive in the evolving world of programming. These lessons help you learn by actually doing it. This hands-on method has proven to be 6 times more effective than just watching a video about it. From learning Python to developing an intuition for computer logic, you'll get hands-on experience with real programs and learn to think like a programmer. Instead of just passively watching videos, you'll actually learn by doing, solving problems, and practicing concepts hands-on. This is up to 6 times more effective than passive learning. Beneath the hundreds of aircraft are the crew mess and ship's galley-designated areas, where military personnel eat, socialize, and sometimes live. This aircraft carrier has 2 crew decks, one forward and the other located here. What's even more unbelievable is that it has a mini supermarket for the roughly 5,000 personnel to shop at their own will. But this floating city needs to sleep, and the cabin crew is spread all over this floating vessel. Quarters can be found both forward and back of the ship, as shown in these visuals. Adjacent to the marine quarters is the engineering hangar for repairing the maintenance-hungry jet engines, and the laundry room is located just below it, along with an equipment room nearby. To accommodate the universal ordnance magazines, they are strategically placed at the bottom of the ship to minimize the risk of explosions, and this storage compartment can extend throughout the entire ship. As you can imagine, this beast is not left unprotected. It can carry two 50-caliber machine guns at the front. Moving a bit further are two phalanx weapon systems on both sides. Additionally, an anti-aircraft Sea Sparrow missile has been added just close to the phalanx. At the back, you will find Sea Sparrow missiles on both sides and a close-in support system like the phalanx or the Sea Ram. Inside this close-in support system is the Q-band search radar. Just below it is the Q-band tracking and gun-laying radar, and beneath that is the 20mm Gatling gun, which spits out 4,500 rounds per minute. All these rounds are fed from the ammunition drum. When a missile speedboat tries to get within a range of about 2 miles, the close-in support system activates and spits rounds, dismantling an enemy boat in seconds. Due to the concept of fast-flying drone warfare like this one, the Sea Sparrow can destroy it with utmost precision. It has a range of around 50 kilometers, which is 30 miles. With a $12 billion price tag, this aircraft carrier has bodyguards. A typical carrier strike group might comprise 5 to 7 of these ships. At the center sits the aircraft carrier. These carriers can accommodate a maximum of 130 fighter jets. Flanking each side are 4 destroyers. They could be the Arleigh Burke-class destroyers, predominantly used for anti-air warfare. Leading the battleship at the front is a Ticonderoga-class cruiser. These ships are multi-mission, covering air warfare, undersea warfare, launching torpedoes, naval surface fire support, and surface warfare. At the back is the frigate class, generally serving as a light escort with a focus on anti-surface and anti-air roles with a lesser degree of capability than larger ships. Depending on the mission, nuclear-powered, Virginia-class submarines animated in our recent videos can also be added to the carrier strike group to seek out and destroy hostile surface ships and submarines. A typical carrier air wing can include the Grumman E-2 Hawkeye. This aircraft flies ahead of the aircraft carrier, scanning the battlefield with its large red radar. Simply put, it acts as a scout, providing early warnings of any enemy activity up to almost 100 kilometers away. They even have a mini cargo plane, the C-2 Greyhound, which they use to transport equipment and personnel. While the 6 Seahawk helicopters are designed for rescue and anti-submarine missions, these Seahawk helicopters can be launched from a specific part of an aircraft carrier. A sonar line is deployed to scan for enemy submarines underneath the ocean water. Upon detection, the helicopter can launch a torpedo at the target. Once launched, the torpedo, equipped with its own sonar system, will actively track and pursue the submarine until it successfully neutralizes the threat. Now, this moving city that weighs around 100,000 tons needs to move. They do that with these 2 nuclear reactors, one positioned at the front and the other situated here. This nuclear reactor is composed of several components. Simply put, this core acts as a miniature sun within the reactor. Additionally, you will find these steam generators and powerful turbines integral to its operation. Let's compare this to a human to help you understand its size. It's important to note that this comparison depends on factors such as the reactor's design, size, power output, and efficiency. This is how it works. These radioactive furnaces create tremendous amounts of heat that boil water. This creates high-pressure steam that helps spin these giant turbines indirectly, powering the carrier's 8 electric generators. Yes, you heard that right. Not 2, but 8 General Electric generators. This could easily power a city of 100,000 people. Using massive reduction gearboxes, the turbines are connected to turn these 4 mammoth propeller shafts that drive the ship, giving it a speed of around 35 knots. which translates to around 64 kilometers per hour. But a quick note here, the actual speed is still highly classified. As nuclear physics is a complicated subject, we'll simplify it for you through these animations. A nuclear reactor consists of three crucial components: fuel elements, which could be uranium-235 or uranium-238, a moderator, which can be water, and control rods, whose main function is to absorb any excess or spare neutrons in the moderator. Let's see how it works. Uranium oxide is compressed into fuel. Parts of uranium are packed into sealed fuel rods. The fission of uranium begins by bombarding it with neutrons. In each fission, 2 or 3 neutrons are released. This, in turn, causes new fissions, thus creating a chain reaction. However, in a nuclear reactor, it's important that this chain reaction is controlled. After each fission, only one released neutron should cause a new fission. This is how it is controlled. By lowering the control rods, they absorb the excess neutrons. Lowering all the control rods at the same time results in stopping the chain reaction. Now that we have mastered the basic understanding of a nuclear reactor, let's look at the step-by-step process. Step 1. The nuclear reactor heats the water to 320 degrees Celsius. Step 2. The pressure regulator is responsible for preventing water from converting into steam. Step 3. High-pressure water passes through a steam generator. This is where you want to convert water into high-pressure steam. Step 4. The steam helps turn these huge turbines at a very high speed. Step 5. The spinning turbines are connected to these gears. Step 6. The gears and clutch then power the electric motor. This, in turn, powers the propellers of this huge aircraft carrier, propelling at speeds of around 35 knots, which translates to around 64 kilometers per hour. The steam from the turbines is then passed through a condenser, which turns it into water. It is then pumped back into the steam generator, and the process is repeated, giving it almost unlimited fuel for this aircraft carrier. We make original 4K 3D animations with a small team of animators. So, please support us by subscribing and dropping in a comment for more exclusive engineering animations made just for you.